All right, so 4-6, the multiplication rule for independent events. So how does that general rule change if we know the events are independent? If we know that the occurrence of one doesn't affect the occurrence of another, right? Independence. Well, here is your multiplication rule for independent events. If I want two events that are independent to happen at the same time, A and B, it's just the probability of A times the probability of B. Now, again, I want to revisit the general rule. So if you revisit the general rule says the probability of A and B, not independent, is the probability of A times the probability of B given A, right? And this is because A happening changes the probability of B. But let's recall that if two events are independent from section 404, then the probability of B given A equals the probability of B. A doesn't matter. This means that they're independent. Well, that's what we're saying right here. So that's why we take out this conditional and just replace it with P of B. And that's exactly where this formula comes from. Okay? So be aware of that. That is just the general rule, but instead of the conditional, it's just the straight probability of the second event because the first event doesn't influence the second event. Okay. Now note right here, we can extend the multiplication rule for independent events to more than two events. So you're going to see what we do in the example. It's going to be more than just two events happening. Okay. So example 1, what factors led to the Challenger disaster? On January 28, 1986, Space Shuttle Challenger exploded on takeoff, killing all 7 crew members aboard. Afterwards, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Experts estimated that the probability that an individual O-ring joint would function properly under the cold conditions that day was 0.977. But there were 6 of these O-rings, and all 6 had to function properly for the shuttle to launch safely. Assuming that O-ring joints succeed or fail independently, find the probability that the shuttle would launch safely under similar conditions. So there are 6 O-rings, and they all had to function properly. All 6 had to function properly for a safe launch. And again, we are assuming that they're independent. So let's use R for O-ring. So the probability of a ring working was 0.977. Well, we need 6 of them to work. So we need to find the probability of all 6 rings working. Well, that's going to be 0.977 times 0.977 times 0.977 times 0.977 times 0.977. I can't even write it. It's like write my signature over and over. It just gets worse and worse. Times 0.977, right? 1, 2, 3, 4, 5. There are 6 0.977s. We can write this a little bit more savvy, can't we? We should know our exponent rules. This is just 0.977 to the 6th power. And I'll just type that in a calculator real fast. 0.977 to the 6th power gives me, and I'll round to 3 decimals, 0.8. Now it's 696, so the 6 makes the 9 become a 10, so it's actually, so I'll write it down, so it's 0.8696. So the 9 rounds up to a 10, so I really get 0.870. So there we go. All right, so that's the probability if I were to round to 3 decimals. Again, if you forgot the 0 at the end, I wouldn't really care. Okay. All right, so that's the first objective. Pretty short and sweet. Second objective's coming up.